Imagine you are tracking daily financial returns. Some days you make a profit, other days you take a loss. If you string enough bad days together, your overall balance drops into the negative. From that point on, any new profit first has to dig you out of that hole before you actually start building wealth. Look at this line graph. Your balance is climbing, then takes a sharp dive into the red. But if you reset your balance to zero the moment it drops below the axis, you stop the debt from dragging down your future earnings. You clear the losses and start the next sequence with a clean slate. Standard programming often overlooks this simple shortcut. To find the highest possible continuous sequence, the maximum subarray sum, the default brute force method calculates every single possible combination. It wastefully checks overlapping sequences it has already measured. This side-by-side comparison shows the difference. On the left, the brute force method recalculates every overlapping sequence from scratch. On the right is Kadane's algorithm. By walking away from debt, it solves the problem in a single pass from left to right, finishing the job in milliseconds. A negative running total can never contribute to a higher maximum score. By dropping bad sequences immediately, we stop looking backward and scan the data exactly once. Here is a sequence of numbers. To execute Kadane's algorithm, we only need to track two variables. First is our current sum, the running total of our continuous sequence. Second is our max sum, the highest overall total we have found so far. We step to the very first number, a 3. Our current sum updates to 3, and since it is the only number we have seen, our baseline max sum is also 3. Now we move to -4. Adding this drops our running total to -1. We have entered into mathematical debt. If we carry this -1 forward, it will only reduce the value of whatever numbers follow. So we apply the core rule. The moment the current sum drops below 0, we reset. The algorithm zeroes the tracker out. Now we have a clean slate. We add the 5, and then the 4. Our current sum jumps to 9. We compare this against our previous maximum of 3 and update our max sum to track this new high. This is dynamic programming. Instead of analyzing the entire dataset at once, we solve for the best possible sum at each individual step. Resolving these tiny local problems eventually reveals the global answer for the entire array. But consider a different scenario. What happens if the array consists entirely of negative numbers? Handling this scenario requires following a precise order of operations, specifically to ensure the algorithm doesn't ignore the data when every option is a loss. Look at this logic flow. If the algorithm resets a negative sum to 0 immediately, it will return 0 as the highest sum. But in this array, 0 doesn't exist. The logic has invented a high score that isn't in the data. The correct answer for an all-negative array is the smallest negative number within it. To find it, the code must be able to record that negative value before the reset happens. We solve this by strictly sequencing the code. Step 1 is always adding the next number to the current sum. Step 2, immediately update the maximum sum, capturing the highest score even if negative. Step 3, evaluate the debt. If the running sum is below 0, reset it. Placing the reset at the end ensures legitimate negative maximums are recorded first. This establishes the logical sequence for the algorithm. Add the next element, record the new maximum, and finally, reset the current sum to 0 if it has fallen into the negative. Kadane's algorithm shows that we don't need to look at every possibility at once. By making one optimal decision at each step, even the most complex data patterns become a simple linear walk.